Hi everyone, let's talk about homework 7. And this is also our last homework. So if you're pretty satisfied with what you got in previous homework, you don't have to actually do this one because the lowest score will be dropped anyway. So in this homework, we are going to focus primarily on 2x2 contingency table. We have developed 3 different ways to calculate or to compare P1 over P2. The first way obviously is to get their difference, P1 minus P2. And the second one is P1 over P2, and we give it a name, relative risk. And lastly, we also talked about what is odds ratio and how to calculate odds ratio. So you are supposed to know, for instance, how to use R to calculate odds ratio and how to find a confidence interval for odds ratio or do a hypothesis test for odds ratio. Lastly, if you are having a contingency table of higher dimension than 2x2, maybe 3x3 or 4x4, in that case you just have to do a chi-square test. So without further ado, let's get started. So the first one is about the hypothesis test, but you are supposed to state the null hypothesis in words. So in words, the null hypothesis should be the striped and the red forms, they survive equally well. And of course, if you are asked the alternative, it should be the red form survives better than the striped form based on the background information. In order to get the null hypothesis in symbols, you can just say H0 is P1 equal to a P2. But you have to specify what P1 is and what P2 is. Specifically, P1 means the probability of a striped species can survive, and P2 means the probability of survival for the red fish. You can have a 2x2 contingency table depending on whether your fish is survived or died, and also depending on is it striped or red. So you can have a contingency table like this, and if you want to mimic what the author was doing in 10.1.2, you just have to calculate the survived rate for each of the group. So you only have to fill this cell, which is given by 65 over 65 plus 98. And similarly for the red group, you do the same thing, which is the individuals that have survived over the total counts of individuals, which is 23 plus 18. So that is how to do part 3 of this question. In order to find the p-value and test statistic, we have 2 routes that we can go. We can either do this by R or do this by hand, but here in this example we are gonna demonstrate how to do this by hand. In later examples I'm gonna show how to do it in R. So in this one, the paradigm, the mental paradigm is to compare what you expect and what you really see and find the discrepancy between these two. So what are we expecting? Our expectation is in line with the null hypothesis. So we are assuming that the P is the same across the striped group and the red group. There is no difference between these two. Or in other words, there should be a universal P in terms of survival across these two groups. So we can calculate that universal P by adding up 65 plus 23, which is the total number of survivors, and divided by the total counts. If you do the math, you can get something around 0.43. And that is the universal P, and that proportion should be applied to both striped group and the red group if your null hypothesis is true. So what we are going to do next is we are using this 0.43 multiplied by 163 because we have 163 of the striped individuals. If we multiply 163 by 0.43, what we got is the expected number of survivors, and we can fill in that number into this cell. So if you do the math, it should be 163 multiplied by 0.43, and the number should be 70.31. What about this part? You can just use 163 minus this 70.31 and you can get 92.69. You can apply the same logic for the second group because this is universal P. It should be able to apply to both of these groups. So you use this proportion, multiply 41, put it in this cell, and the number it should be 17.69. And similarly, you can find the number of this cell by 49 minus 17.69. You get 23.31. And lastly, to wrap this up, you have to find the difference from between the expected and the real value. and square them and divide it by the expected, and that is going to follow a chi-square distribution with degrees of freedom 1. So this is how to calculate the whole quantity. For example, if you focus on the first cell, you got 65 subtracted by 70.31, which is expected value. Do you square this difference? Don't forget to divide this whole squared quantity by the expected value, which is 0.31. For each of the 4 cells, we have to do the same thing. So you see there are 4 quantities, and if we add them all up, copy and paste them in R, so we can end up with chi-square statistic. If you type everything in R and make sure everything is right, so you can get 3.508 something as the test statistic. So that's how to find it. Okay, next up we have to find out the p-value under this distribution. By definition, p-value is the probability of seeing some value that is even more extreme than you have observed. And in this case, you are supposed to see something that's greater than 3.508 under this chi-square distribution. By the way, this is a chi-square distribution with 1 degree of freedom. So we actually want to find the probability under a chi-square distribution, but we want to find the probability of your chi-square variable greater than 3.50 something. So we use 1 minus, and this is the value, but don't forget to specify the degrees of freedom, because as you change the degree of freedom, you will end up with a different distribution. So you have to specify this. This is mandatory. But this is not the end of it. Remember, in the beginning we mentioned we want a one-sided test instead of two-sided. We have to consider the direction. And in order to understand this, I advise you to read the last page, literally the last page of your textbook, which is table 9, in which it says if each alternative is directional, which is only possible when degree freedom equal to 1, the directional p-values are found by dividing the column headings in half. And that means in order to get the p-value for the directional chi-square test, we have divided the existing p-value that we have just found by 2, like this. The p-value for this specific question is supposed to 0.03. And last but not least, in order to answer the question in the context of this problem, you are supposed to say we are going to reject the null hypothesis, and there is sufficient evidence because our p-value is smaller than 0.05. So we are able to conclude that the red form survives more successfully than the striped form. So the following one, 10.2.5, is identical to the previous one, 10.2.4, but in this question I'm going to solve it in R, so you guys can have an idea, like if I want to do it in R, how should I do it? First of all, we have to type in the contingency table. It has more than 1 dimension. That is why we have to use a different data structure. Here we call it matrix. So we can give it a name. Let's just say weight equal to matrix, and we have to pass in our data. And let's do this by column. 11, 15, 17, and 4. And we have to specify the number of rows is 2. So if we take a look at the data that we have just typed in, we get something identical to the textbook. What we want to do next is a chi-square test. We pass in our data here. Just one thing, we have to turn off the correct option, because the yes continuation correction is not something what we want. So let's turn this off, make it to false. We can get the result. But in R, the chi-square test have only one option as being two-sided. We cannot have like one-sided option when we are doing a chi-square test. But the textbook explicitly asks you to do a directional alternative following the 5 steps. What we have to do is we have to manually divide this p-value by 2. And this is the true p-value that we want from the directional hypothesis test. I'll trust you guys with everything else, because you have to complete the 5-step hypothesis procedure based on the output here, like state your null hypothesis and provide the test statistic. In this case is this 7.20 something, and state what the p-value is, and state the conclusion and explain the conclusion in the context of this specific problem. Okay, this is how to type in all the data in 10.5.7. So in this question, the only difference here is we have higher dimension than 2 by 2, and this is obviously a 2 by 4 contingency table. So this is how to put in the raw data here, and then we change this raw data into a matrix by a matrix function, and don't forget to specify nrow equal to 2 because we have 2 rows. If we run these 3 lines of code, actually I already did, you have the contingency table which is identical to what we had here. So you want to use chi-square test function and put in the eating disorder and turn off the correct option. You got the test statistic or chi-squared statistic, which is 1.8337, and degree of freedom equal to 3, and p-value is 0.68. You have to accept the null hypothesis, or you fail to reject the null hypothesis because your p-value is not small enough. So combining the context, we can say there is insufficient evidence to conclude the treatment group and the condition are related. Next up, 10.7.1, you don't have to organize or reorganize your data into a contingency table. You only have to figure out for each of the group how many successes you are going to observe. In the placebo group, you observed 139. This is the total counts of placebo group. So this first vector is a vector of successful trials you see, but actually in this case they are not successful trials, they are just new fractures and whatnot. The second vector is about the total trials. So that is the total trials of placebo, and that is the total trial of treatment group. If you want to get the exact result, and also remember to turn off the correct option, because this option works for small sample size, but in this case obviously we have like more than enough observations, so make sure to turn this off. So if we run this line of code, we can get a 90% confidence interval that ranges from 0.018 to 0.07. That is the 95 confidence interval for the true value of P1 minus P2. And the following question is kind of identical, so make sure you pass in the number of successful trials and make them in one vector, 32 and 20, and also pass in the number of total sample size of each of this group. And because we have a relatively large sample, so we don't have to worry about the correction, so make sure to turn this off. And run this line of code, we can get the 95 confidence interval, which is from 0.029 to 0.2327 something, and that is the difference of P1 minus P2, from which we can actually conclude that the confidence interval actually suggests that bed rest may actually be harmful, because if we compare these two groups, the group of women who stay in bed have a much higher likelihood to have preterm deliveries. First, recall the definition of relative risk, which is P1 over P2. So let's calculate P1, which is given by 3995 divided by the total counts 46941, and that is P1. And P2 is, that is 221 over the total counts, which is 5228. And you got P1 and P2. In order to get the relative risk, you just use P1 over P2, and that is relative risk. For the next question, 10.9.4, we are still using the data from the previous question, but we want to calculate the value of odds ratio. Obviously, you can multiply the main diagonal line, which is 3995 multiplied by 507, and divided by the product of the secondary diagonal line, which is 221 multiplied by 42,000 something, and that will be the odds ratio. On the other hand, you can also do everything by R. The R function that can handle everything for you in terms of odds ratio is Fisher.test. So before we do this, we have to make a matrix that looks identical to the contingency table that we got. Let's call it docs and take a look at the docs. Use the Fisher.test function and just pass in docs as the only argument. So everything here in this result is about the odds ratio. For instance, this is the confidence interval for odds ratio, and this is the point estimate for odds ratio, and you can also get a hypothesis test for odds ratio. The p-value here serves for the purpose of hypothesis test. In part B, we can conclude that a 95 confidence interval for the population value of odds ratio is between 1.83 to 2.43. So that concludes part B. And in terms of part C, we can say something like we are 95 confident that the odds ratio of hip dysplasia for golden retriever is between 1.84 and 2.43 times greater than the odds of hip dysplasia for border collies. Remember, this statement has to be about odds. It is not about probabilities. However, because the hip dysplasia is somewhat rare, so we could also say that we are approximately 95 confident that golden retriever are between 1.84 and 2.43 times likely to get hip dysplasia than border collies. But this is not 100% accurate because the odds and probability, they are different quantities conceptually. So I'm going to skip 10.9.6 because the first part is identical to the previous one. You can either do this by hand or in R, and step 2 can be solved by Fisher dot test. Maybe you might have some question about part C. What you can say is the numbers are small, but the confidence interval takes this into account. If we have more data, we can have a much shorter confidence interval, but in this case we are having a wider confidence interval because we don't have enough data, but that has been accounted by the length of the confidence interval, so you don't have to worry about that. And on the other hand, the confidence interval, because it does not include 1, we can be quite confident that taking this drug is associated with the increase of odds of a stroke. The first part asks you whether or not you think the null hypothesis is true, so you have to know what the null hypothesis is. Basically, it says all the mu i's or the group mean of each of the group, they are the same. You can just eyeball them and give initial guess whether mu1 equal to mu2 equal to mu3. I don't know about you, but it appears to me that group 1 is shifted up from the others, and thus H0 is not true. So the second question is about ANOVA table, and in ANOVA table you have to understand how many what the degree of freedom is. Actually, there are 3 of them. The between degree of freedom is k-1, in which k is the number of categories or the number of groups. In this case, we have 3 groups. First degree of freedom, which is degree freedom of between, is 3-1, which is 2. And the second one within degree freedom is n minus k. So you have to figure out what is n, which is 42, which is the number of individuals in your sample, and k is number of groups, which is 3. So you got 42 minus 3. That's why it's 39. Total degree of freedom is actually just n minus 1, in which n is the sample size. So 42 minus 1, you got 41. You got 3 degrees of freedom for the ANOVA F-test, and they are 2, 39, and 41. And to calculate the F value, you only have to find out 2 quantities, the mean square for in between and the mean square for within. So you have to get the ratio of 68.06 over 10.72, and that is 6.35, and that is the F statistic. Lastly, in part D, we are supposed to give a conclusion based on the comparison of p-value and alpha. So we don't have to bother calculating that because it's already a given, which is 0.004. And we want to compare that with alpha equal to 0.05. You know the drill, because it's too small, so we have to reject the null hypothesis and embrace the alternative. And that is why we can say there is sufficient evidence to conclude that the mean MAO level is not the same for all the 3 groups. This one is like just doing 11.4.2 in a backwards manner, because it asks you the number of groups, but you were given the table. In the group degree of freedom, you get 2, and you know that you get this degree of freedom by k-1, where k is the number of groups. So k-1 equal to 2, so you know that k equal to 3, and you got 3 groups in this ANOVA table. And in part 2, we just have to compare the p-value here with the 0.05, and the p-value is given in the last column, which says a prob, which is 0.68. Since 0.68 is way greater than 0.05, there is insufficient evidence to conclude that the population mean yields of the 3 different groups are different.